Welcome back. Today we're talking about the incenter of triangles. We're going to focus our attention on right triangles today, so that will make our work a little bit simpler. Some of these techniques don't work for triangles that don't have a right angle. But really, we're going to showcase a sequence of different techniques and strategies for solving some geometric problems. And these strategies are available in lots of different contexts geometrically, and I want to call your attention to the profound differences in the attitudes that are represented by these different strategies here. So let's remind ourselves what this problem means. We have a triangle. In this case, we have a right triangle, and it has dimensions 3 and 4 and 5. That's the simplest right triangle we often have in lots of high school mathematics. And we want to find its incenter. Let's remember what the incenter is. The incenter is the center of the inscribed circle, the largest circle that can be drawn inside the triangle, and it will be tangent to all 3 of the sides of the triangle. That's the incenter. We want to find its center. We want to find the coordinates of its center, I guess. We also implicitly here, we want to find the in radius, which is the radius of that circle, which can be inscribed in here. And so we're going to explore some strategies for how to find this out. The incenter is also, as you'll recall, the intersection of the angle bisectors. And so I've talked about the incircle, but the incenter is also obtained by drawing these angle bisectors here and here and here and finding where they intersect. So I can just, freehand these guys here, draw this angle bisector, draw this angle bisector. A theorem says they will all intersect at a point, but my diagram is imperfect, so I didn't quite get it right. So they will intersect somewhere around here, right? If I shade this point big enough, it hides the inaccuracies of my diagram. So this is actually one of our techniques, and I want to call attention to what I'm doing here. I'm drawing and attempting to estimate the solution to the problem by hand. And so this is what I will call the empirical method here. We're going to try to solve the problem, where is the incenter of this rectangle, empirically. Now, in order to do this, we need to start with a decent diagram here. So I've started with what looks to be a right triangle. This is 16 inches. This is 12 inches. This is about 20 inches. So with 4-inch units, this is a 3, 4, 5 unit right triangle. I've tried to sketch it so that it is in fact a right angle here, but all of these measurements are approximate. And now what I'm doing is I'm effectively using the picture that I've got to solve the analytic problem. I'm basically trying to eyeball where these angle bisectors will meet. I'm trying to eyeball where the circle will be, right? But nothing about my picture is perfect. Not only is this an imperfect circle drawn in there, this is an imperfect, these are not quite in the right ratio. This is not quite a right angle. Everything about the diagram is imperfect. But I can still use the diagram to estimate an answer. And you'll notice here that we can identify an incenter this way, and quite clearly looks like, if you mark it out here, it looks like it's about at coordinates 1, 1. That is, if you take this to be the x-axis, and if you take this to be the y-axis, and if you take this to be the origin, this looks like it's about 1 unit. So this is 4 units, but this is about 1 unit over, and that's where this is. This is about 1 unit up, and that's where this incenter seems to be. And so it looks empirically like the incenter is landing at approximately the coordinates 1, 1. Now, this is a valid method. It just isn't a perfectly precise method. It answers the question by measurement. We can't hope to prove that the answer is exactly 1, 1 by this method, because this method is so sensitive to all of the measurement errors. So, but I do want to point out that this is, this is relevant information, right? Empirically, about 1, 1. So this is a technique that we don't use a lot in higher mathematics because we want to be sure that we're right instead of approximately right. We want to be exactly right. And not only do we want to be exactly right, we want to know that whatever we do that turns out to be exactly right is the right method. And we haven't messed up our method. We want to know for sure that that really is the right method. So, so we don't often use the empirical method in geometry, and for good reason. But it is a way of accessing some information. It's a scientific and realistic way of doing it. I want to remind you that geometry is supposed to be perfectly rigorous, right? And it's sort of perfectly abstract in the sense that the lines are perfectly straight and perfectly thin, and the points have no actual, height and width, so they're perfectly small, they're perfectly precise locations and all of this. So geometry has this abstractness to it that it can only, this perfectness that it can only get from that abstractness. However, geometry is supposed to be a model of real world things, right? And when we think about this perfect 3, 4, 5 right triangle, this is supposed to be an imperfect reflection of it. And so this problem has some correct mathematical solution. This empirical solution should be pretty precise. It should be pretty, it should be close. So this is not a completely crazy method, but it isn't enough. So this is our empirical strategy. And that's an interesting strategy, and it's always available to you. If you think like you don't know where to get started on a problem, you really just don't know how to begin, then maybe just draw a really good, precise diagram and let the diagram tell you what the answer is. And then you'll say to yourself, oh, yeah, okay, maybe that makes sense, right? Maybe I can prove that it's 1, 1. Like maybe this is a strategy for formulating an initial guess that we can then later prove. Okay, so it's not a strategy that we often use in higher mathematics when we're trying to do higher geometry, but it is a valid way of getting a little bit of information about our situation. So what's our next method? I want to use trigonometry. So the next method is going to use trigonometry, but it's also going to use planar algebraic geometry or analytic geometry because we're going to be writing equations for shapes. So let me explain how that's going to go. So let me remind you, of course, that the incenter is the intersection of the 3 angle bisectors here, which I've suggested by drawing these lines. Now I'm going to eyeball one of the angle bisectors, and then we're going to try to figure out what its equation is. So this is my attempt to draw in one of the angle bisectors. And I think I'm actually going to put it in a slightly different color here to highlight its difference from the other lines in the picture. So let's focus our attention on this angle bisector. Now, we know that this is part of the information that we need to know about in order to get the incenter. We know that if we take 2 of these angle bisectors and intersect them with each other, then we will get the incenter. So let's just imagine, can we figure out how to get the equations of these things? Well, there are 3 of them to work with. And, well, surprise, one of them is really easy to find the equation of, because this is the angle bisector of a right angle. So because we have this right angle here, and because we've chosen the coordinates here so that this is the x-axis and this is the y-axis, then this is just making a 45-degree angle to the axes. And this has a very simple line equation. And this line equation is y equals x. Slope 1 through the origin, y equals x. Right away, you can see something profound is happening. We're not doing pure geometry here. If I'm writing equations for the lines in the figure, then I'm actually doing analytic geometry. I'm using coordinate geometry. And so this is a really easy line equation to find, but I want you to sort of notice that we've kind of exited the realm of pure geometry. Let's only reason about angles and lengths. And we've entered the realm of now we're using coordinates to describe these shapes. Can we continue this? Well, yes and no. We will find the incenter here if we can find the equations of the other 2 lines. And in fact, we only need one other line in this picture, because then we can find the intersection point of 2 lines and not even be concerned about the 3rd line. So let's try to find the equation of this line. So I'm going to identify that. What's the equation of this line here? Well, that's not so easy. Let's label some letter labels on these points so that we can talk about them more precisely. Let's call this C. Let's call that A. Let's call that B. And let's call this point over here, which is the point formed by the angle bisector, let's call that Y. Because often when we're talking about Chevians, the Chevian that connects B to the opposite side is BY. So now we have some labels for these points. We want to find the equation of the line BY. So we want to find the equation of BY. How are we going to do that? Well, if we had the coordinates of the point Y, then we'd be good to go, but we don't. We could eyeball the coordinates of the point Y, but then we would really be back to the empirical method, right? If I want to say, oh, that's about 1 or that's about 1.5, then I'm really just doing this empirically, and I'm trying to get away from doing this with imprecision. I'm trying to do this perfectly precisely. But but caution, I won't be doing this absolutely perfectly precisely, as you'll see soon. How can we find the coordinates of this point y? Well, what we're going to do first is we're going to do it by means of some trigonometry. So let's look carefully at this line. Do we know anything about this line? Well, we know that this line is an angle bisector. So the angle formed here, CBY, here, is exactly half of angle B. And that could be useful if we knew angle B, but we don't know angle B, but we can get it using trigonometry. So let's use a little trigonometry to get B, to get angle B, and then we'll divide that angle by 2 to get angle CBY, and then we'll try to use that to our advantage. So this is how we're going to use a little bit of trigonometry to deal with these angles. So if I take the tangent of angle B, then that's going to be 3/4, because the tangent of an angle in a right triangle, and this is a right triangle, is the opposite side length divided by the adjacent side length, and so that's going to be 3/4. And so if I want to get the actual measure of angle B, then that's going to be arctan of 3/4. And I can use a computer or something to calculate the arctan of 3/4. And I did that a little bit earlier. So the arctan of 3/4 is about 0.64. So that's about 0.64. Now notice that approximation sign. That is going to be significant here. I don't want to underestimate the significance of the fact that I just made an approximation, right? Compared to the empirical method, which I said was imperfect because it's approximate, if this arctangent is not exactly 0.64, and it's not, then I have just introduced a source of error here, just as I did in the empirical way of thinking. So what does that mean about angle CBY, which I've highlighted in pink here? That means that angle is half of that. So that's arctan of 3/4 over 2, which is approximately equal to 0.32. Now, is that any good to us? So that's radians. It might not, it looks like it's a lot more than 1 degree, but that's in radians. So is that any use to us? Well, yes, because if we know this angle, then we can use more trigonometry to find the length CY. So how can we do that? We know that the tangent of angle CBY is equal to the length CY over 4, because the tangent of that angle is its opposite over the adjacent. And so we get this thing divided by this thing. So this unknown CY divided by 4 is the tangent of that. So what I need to do now is I need to take the tangent of 0.32. So that's the tangent of 0.32, and that's going to be CY over 4. And then in one step here, I'll just move the 4 to the other side. And then that I can calculate on a computer. And when I ask the computer what is that value, I get a decimal. And so I ask the computer to do this, and it says CY is approximately 1.33333333. Now, this is peculiar. So actually, I'm telling a little bit of a lie here. On the chalkboard, on the whiteboard, I kept 2 decimals of precision only, and rounded this off. But on the computer, I kept many more decimals of precision so that I would get a more accurate answer. And I got, so if you're following along and put that into the calculator, you might not get something quite so exactly equal to 1.33333, but in the computations that I did, I was more precise than suggested here, kept more digits, and I ended up getting CY equals 1.33333. Now, I don't know, because this came out of the computer, I don't know whether the next digit is another 3, which it probably is, or an 8. I really don't know. And that means that no matter how many digits the computer gives me here, and being all 3s, I might suspect that this answer is really honestly 4/3, but I don't know that for sure. And so I still have this approximation here. So this looks like this is the point whose coordinates are 0, 1.3 repeating, but I don't know that for sure, and because it's an estimate. All right, that gives us the coordinates of this, and on the basis of that, we can find the slope of this line, and then find the equation of the line, and then find where it intersects that. So let me illustrate that, because we're going to need that in both of these situations. So so line BY has slope. So the rise here is -4/3, -4/3, and the run is 4, so that's over 4. And so that's the 4's will cancel, of course, and that's -1/3. And so the equation of line BY is going to be y equals -1/3 x plus 4/3. And again, I'm not completely sure that it's 4/3, but it kind of looks like it's about 4/3, so I'm going to round it off to 4/3. So that gives me the equation of this line. I already have the equation of this line. So I'm going to simultaneously solve. Y equals -1/3 x plus 4/3, and y equals x. Now, I just want to call your attention to the fact that this no longer feels like geometry. It feels like this is happening in a high school algebra course. And in a sense, this is high school algebra, right? There is really no fundamental difference between this and high school algebra. That means that in a sense, we're doing the geometry in an impure way, but the coordinates are very, very powerful. Coordinate geometry is a very powerful tool for getting this work done. And so this is a good thing. When this is done in high school and even in higher levels, we should not be so dedicated to separating these things, right? Geometry is algebra. Algebra is geometry. We shouldn't try to peel these things apart too hard. On the other hand, there are powerful techniques in pure geometry that we're not using here, and they would make this problem work out better. And so it's useful for us, it will be useful for us to revisit this in a bit. So here we need to simultaneously solve these equations. And because this is just an algebra problem now, I'm going to do this fairly quickly. So I'm going to take, since these are both equal to y, I'm going to set them equal to each other and solve for x. So x equals -1/3 x plus 4/3. I'm going to add 1/3 x to both sides. X plus 1/3 x equals 4/3. X and 1/3 x is 4/3 x. So 4/3 x is 4/3. And finally, I get x equals 1. So that's what I get there. So I'm going to close this blind to reduce the glare. So we get x equals 1. What is y equal to? Well, one of my equations is the equation y equals 1, x, and so I get y equals 1. And so the coordinates here, so the in-center is the location 1, 1, and the in-radius is the radius of a circle centered at 1, 1. Notice that circle is tangent to the x-axis and tangent to the y-axis, so its radius must be 1. So the in-radius is 1. And I find this, you should find this perhaps remarkable, perhaps suspicious. Maybe that's the same thing mathematically. What's remarkable about this is that we ended up with a tremendously simple answer. It's the location 1, 1, and the radius is just the number 1 here. After we went through the arctangent of 3/4 and we got 0.64, and we managed all of this decimal gobbledygook. So that's suspicious. Maybe it seems miraculous. Maybe it's because math is amazing, and yeah, math is amazing. It might mean that our technique was more complicated than it had to be, right? When the technique passes through this complicated gobbledygook and ends with a simple answer, then you should always be somewhat suspicious that maybe the technique itself was a circuitous route. Maybe there was a shortcut that made this easier. And in this case, yeah, there is a shortcut that makes this easier. So but this is a valid way of doing it. This is very much an analytic geometry approach because we're using algebra with the line equations themselves, which is not typical in a pure geometry situation, but is totally a valid method. And we're using trigonometry here. We're using it really hard. One of the things you need to notice about this is that I could not have done this, at least not in any obvious way. I could not have done this without a computer, right? I needed the computer to calculate the arctangent of 3/4, which I don't have memorized, and who does, right? I needed the computer to calculate the tangent of this other angle here. So this is very much a computer-heavy approach, and I don't want you to underestimate the difficulty of calculating the trig functions. It's really hard to calculate the values of trig functions without a computer. So like if you roll us back in time a few hundred years, then this might be the kind of technique that really doesn't fly because it's just too hard to calculate the values of these trig functions. So that's a serious technique. That's a serious critique of this technique. The complexity of the intermediate work is a serious critique of this technique as well. And so, so there are some things that we need to be worried about here. Now, what I want to do next is, so we've illustrated the empirical, and we've illustrated a solution based on trigonometry and analytic geometry. I want to go on to the law of signs strategy first, next. So this is going to be a similar technique, and I'm actually going to preserve all of this work and try to get the work done in this small amount of space here, because there's something actually a little bit similar about the way it ends, right? This is trigonometry plus the lines, law of signs and proportions plus the lines. So let's do something different. So for this next technique, and if you're going to look closely at our textbook, Geometry Revisited by Coxer and Greitzer, then you'll see this theorem proven in section 1.3, and I'm going to give a quick reproof of it for the purpose of explaining how to calculate this incenter. I want to focus just on this line, which here is by. And I want to focus not on the angle CBY, but on the two angles made at y. So I'm going to call this, so I'm going to forget the value here. And then I'm going to call this theta, and I'm going to call this 180 minus theta, because together they make a straight angle on the y-axis. Now, there is something that we know. Oh, I'm going to call this x. Because, no, I better not call it x, because x is my x coordinate, so bad idea. Let's call this beta, because it's near angle B, it's half angle B, so let's call that beta. So what we're going to do here is we have a triangle CBY, and we have another triangle YBA, and both triangles will satisfy the law of signs. And so and both triangles have an angle beta. And so this is interesting, and what we're going to do is we're going to see what the law of signs tells us about both of these triangles. So what does the law of signs tell you? Well, it's complicated, but it tells you that the ratio of a side length divided by the sine of the angle opposite that side length is constant around the sides of the triangle. So, so the law of signs for triangle CBY tells you a lot, but in particular, it tells you that CY over sine beta is equal to, where is it? CX? Is that X? No, that's CB. CB over sine theta. Okay? So that's something that the law of signs tells us. It also tells us that that's equal to this thing over the sine of 90, but that's not important right now. Okay, what else do we get here? So let's apply the law of signs for triangle ABY. And what will that tell us? That will tell us something about AY over sine beta. Notice that's the same sine beta. And that's going to tell us that that's equal to AB over sine 180 minus theta. Now, what we're going to do here is we're going to focus on what we know and what we want. I want CY. I want AY. I basically know CB. CB is 4. I know AB. AB is 5. I don't know anything about the angle B, and therefore I don't know anything about the angle beta. And so I'm totally eager to cancel the angle beta. So what we're going to do here is we're going to divide these equations. with the idea that the sine betas will cancel when we divide them. So let's do that. We get cy over sine beta over ay over sine beta is equal to cb over sine theta over ab over sine 180 minus theta. Now, it looks like this is still really complicated, but a lot of cancellation is about to occur. Some obvious, some not so obvious. First of all, we've got a sine beta here and a sine beta here, and they will cancel each other. But here, we have a sine theta and a sine 180 minus theta. And the function sine has this symmetry that sine 180 minus an angle is equal to sine of that angle. And so sine theta and sine 180 minus theta have to be the same thing. And that's one of the reasons we did it this way. So these signs also cancel. And that's kind of remarkable here. All the trigonometry drops out and we get a ratio between the lengths. And so we never actually, notice we never actually had to calculate the values of any of these sines or arc sines of any of these angles. And that's important in this strategy. So that makes this strategy more abstract and also more general than the other strategy. So cy over ay equals cb over ab. So cy over ay equals cb over ab. In other words, the ratio between these lengths is equal to the ratio between these lengths. And we know the ratio between these lengths is 4 to 5. So that tells us that the ratio between this and this is a 4 to 5 ratio, which doesn't exactly tell us the coordinates of the point y, but it certainly is helpful for trying to figure out the coordinates of the point y. I should point out here that I'm proving this in the context of the assumption that angle C is a right angle, but I haven't actually used that assumption. This is a general statement which is true whenever you bisect an angle in a triangle. So it doesn't actually, for this argument so far, we're not actually even using the fact that the angle C is a right angle. Now, is this useful for calculating the coordinates of the point y? Absolutely, because it gives us an equation for cy. And because we know that ay plus cy is 3, right? Because this is a 3, 4, 5 right triangle, this larger length here is 3. So we actually know two things about cy and ay. We know this, we know that they sum to 3, and we know this about them. And having all of that together is enough. So let's use this together with the fact that ay plus cy equals 3, and let's use that to solve for cy. I think it's going to be a little bit less confusing if instead of using like ay and cy, if I just use single letter labels for these lengths. I don't want to use x and y because they're in play. Let's call this length u, and let's call this length v here. So cy will be u and ay will be v. So what does this say then? This tells us that u over v is equal to 4 over 5. And this tells us that u plus v is equal to 3. All right, let's cross multiply this. So that gives us 5u equals 4v. Let's solve for v here. U is 3 minus, well, I guess we'll solve for u. U is 3 minus, actually, no, I think I want to solve for v. Sorry. So v is 3 minus u. And then I can plug that in here. So we get 5u equals 4 times 3 minus u. And that tells me that 5u is 12 minus 4u. And so I've run out of room here. Sorry for my poor strategy, but I just have a little bit left to do. I'll add 4u to both sides. 9u equals 12. And then I will divide both sides by 9. U is 12 ninths, which is 4/3, which is supposed to remind you of the last technique, right? 4/3 was the coordinate that we got by our technically estimation methods using trig. But now we've got it exactly, and we know that it must be exactly 4/3. So this is a way of putting the equations from the law of sines together with our prior knowledge that these sum to 3 and getting the value of this length. And now we know that it's exactly 4/3. Now that we know that it's exactly 4/3, then, well, we carry on with this work, right? That identifies the coordinates of this point exactly, just as we did before. And now we confidently find the equation of that line and compare it with this other line, which is the diagonal line up this way, find their intersection point. We just repeat all of this work, which is why I was saving that on the chalkboard. All of this work here follows, and we get the coordinates 1, 1. However, in this case, we know for a fact that those coordinates are exact, 1, 1. All right, so that's how we get, that's how we use the law of sines, and we have a precise method here. It is based on trigonometry, but notice that the trigonometry cancels and we don't actually have to calculate anything trigonometric. This is closer to being a pure geometry argument because we didn't actually have to calculate those trig functions. And so this kind of argument you can do without a calculator. We can complete this without a computer, right? I mean, it's complicated, but we never had to use a computer because we never actually had to calculate these trig functions or their inverse functions. And so that makes it different. So this is closer to being a pure geometry argument. Finally, I want to talk, so it still is a little bit suspicious. The work is very, very, very complicated, and we end with a suspiciously simple answer. And so I want to talk finally about the simplest method for finding the coordinates of the incenter here. And that is to focus not on the coordinates, not on the angle bisectors, but on the inscribed circle and the properties that it must have. So, so next what we're going to do is we're going to put aside all thought of trigonometry, all thought of doing complicated algebra, and we're going to attempt to do a purely geometric solution based on area, which is a totally different way of thinking. So in this problem, it's really the right way to go about it. So let me erase what we don't need, and then we'll get to an area solution. So here we, instead of thinking about the angles being bisected, which seems to be the most important way of thinking in the previous techniques, we're going to think instead about the presence of that incircle. Wherever it may be, there's this incircle here. And the incircle is centered at the incenter, and it has these angle bisectors that come out here and here and here. Now the angle bisectors are rays, and I could continue them here, but what I'm doing here is trying to call attention to a feature in this picture, which is that the angle bisectors, in a way, divide the original triangle into 3 smaller triangles. So, so here we have the original triangle ABC, and if I draw the angle bisectors only to the incenter, then I get 3 smaller triangles. So let's call this point I. Then I want to call attention. So we have triangles ABI, triangle BCI, and triangle CAI in this picture. So basically here and here and here. And now we're going to think about areas, and there's an area equation that just pops right out of this picture. It's less obvious if I continue the angle bisectors, right? If I draw it this way, it looks like we're going to have the area be the sum of 6 areas. But I want to block these off, and I want to think of the area as being the sum of 3 areas instead of 6, namely these areas. So we get an area equation about these things. Now, you might say, what good is an area equation? Well, I would say, good question, because like there's no obvious, the question is not about area, and none of the given information is about area. But let's write the area equation and see what happens. So I'm going to use the parenthesis notation for areas. Area ABC is equal to area ABI plus area BCI plus area CAI. Who can argue that it is, right? That the 3 triangles make up the larger triangle. So, okay, so that's clear. What here do we know and what do we not know? Well, we don't know this, and we don't know this, and we don't know this. And we do know this, actually, because this is a 3, 4, 5 right triangle, and it's really easy to calculate the area of a right triangle, right? So because it has a base here, which is 4, and then it has a height of 3. So this is 1/2 of 3 times 4, or 6, right? So that area is 6. That's easy. Which of these do we know? Well, none of them. And the question wasn't about areas, so you're probably thinking, what on earth is he trying to do here? He's just involved 3 areas, and I don't know any of them. But actually, okay, I don't know any of them, but they all could be calculated on the basis of a common thing that I don't know. So I know that triangle CBI, for example, which is the lowest triangle here, I know that this triangle has 3 possible bases, but one of them is CB. And I know that the height relative to CB is the perpendicular distance from the point I to that base. Now, that perpendicular distance is a perpendicular line here down to the base of the triangle, but it also is a radius of the incircle. And so I'm going to write this as a little r, because that's a radius of this incircle. Now, I don't know little r. That's the thing that I'm trying to calculate. Why am I trying to calculate an area in terms of a little r if I don't know little r, and if little r is what I really want to do? Well, it's because this will at least tell me something about little r, right? It's like when you say, okay, I don't know the age of the person in the story problem, so I'm going to call it x, and then I'm going to try to write down an equation involving x, right? So here, I don't know little r, but I'm going to try to say something about it. And what I can say is that when I have BCI, this triangle, that its area is going to be 4 times little r times, of course, a half, right? 1/2 base height. So this is going to be 1/2 times the base 4 times the height little r. Now let's go over here to the triangle ACI or CAI. This triangle has, as always, 3 possible bases. Let's use the vertical as the base, in which case the height, it feels a little odd to call this a height because it's a horizontal distance, but the height will be this length. And that's another radius. So here the base is going to be 3, and the height is going to be, well, r again. So here we'll get an area of, let's see, CAI here. So here we'll get 1/2 of 3 times r. And then here, you might think this is going to be a very different case because this is the hypotenuse instead of the leg, and I don't have the right angles I need. But actually, this is going to be just about the same. There are 3 possible bases that I can use for the triangle ABI, but AB is the simplest. I know that its length is 5. And relative to that base, the height should be interpreted as this length, the perpendicular distance from the incenter to here, which is another radius, and so that's another r. And so the area of that triangle ABI is, once more, 1/2 times 5 times r. Okay, so what? Well, so let me just, what I want to do here is I want to factor out the 1/2, and I want to factor out the r. So from the right-hand side. So I get 1/2 of 5 plus 4 plus 3, and then times r, the in radius. And here, you know what? I know that this is 6, but I'm just going to write area, because for a different problem, this would just be the area. And so the area, what we're learning here is that the area is 1/2 of, what's 4 plus 3? What's 5 plus 4 plus 3 here? That's the perimeter. It's 1/2 of the perimeter times the in radius r. And now you see, in our problem, the area is 6. The perimeter is, the sum of these numbers is 12. So in our problem, we get 6 equals 1/2 of 12 times r. And you might say, what are you doing? You're trying to calculate area. I want to know the in radius. Now you've got this complicated formula for the area. It involves the in radius, but I don't know the in radius. But see, that's what I'm doing, right? We get a complicated formula for the in radius, for the area in terms of the in radius, and the in radius is the only thing I don't know in this equation. And so we get 6 equals 6r, r equals 1, and that's what we were trying to figure out. On the basis that r is equal to 1, it's pretty obvious that the coordinates of the incenter are simply 1, 1. So that gives us the coordinates of the incenter. This is a pure area argument using a lot of different sort of versions of this 1/2 base height thing from different directions coming around this triangle. So this equation will always be true, even without right triangles. So I just want to call your attention to this. So for any triangle, so triangle ABC, we have the area of the triangle is always equal to 1/2 times the perimeter times the in radius. And that's a handy formula to have. And basically, we're using this formula in order to solve for the in radius because we know everything else. So this is so that's the area logic solution. This is 4 completely different techniques. And I just want you to understand that they use a lot of different ideas. The empirical technique uses the whiteboard itself as a tool of realizing this picture, making the picture real, and then just measuring the reality of it. And that's important. That's a useful and powerful technique, and not to be ignored. The trigonometry and the algebra, both of these solutions, whether we use trigonometry or sort of avoid trigonometry, but also use the law of sines, both of these techniques are coordinate geometry techniques. The coordinate geometry is super powerful, but it tends to give you complicated solutions because you're intersecting lines and you have to simultaneously solve equations in order to do that. And then finally, the 4th technique here that I'm illustrating, I think this technique is very, it's kind of enlightened, but it's also very simple in that the math is really simple. Like, there's hardly anything to compute. This is very much a pure geometry technique. It doesn't matter that this is the x-axis and the y-axis and that these points have coordinates. Nowhere in this technique did we really even refer to the coordinates of anything. And so that makes this technique a very much a pure geometry technique. And in the context of a geometry course, often we prefer the pure geometry technique. But in the wide open world, then we often have a choice, and there are many different approaches that often work. So good luck on your homework. Don't forget that you can have a wide variety of techniques for solving all these problems. If you get desperate and you need to introduce coordinates, just introduce coordinates, find the equations of those lines, and go for it.